So my name is Yotam Gingold, and I want to talk about a compilable markdown for linear algebra that we call I Heart LA. I have the heart up there, although the text is small, because some people say I love LA. Some people think that LA is Los Angeles, but it's linear algebra, and it's I Heart LA is how we pronounce it. But I guess I shouldn't impose that on you. I'm rebranding my lab a little bit. I added another 2 words, computational reality, creativity and graphics lab. The CR, it was hiding in there the whole time. I am interested in all kinds of creative problems, typically involving design, sculpting, drawing, painting, geometry, images, occasionally singing, color, motion, and today I want to talk about scientific expression. So sharing scientific ideas often relies on written communication. This could be in the form of an email that we write to each other with an idea. We could write on a chalkboard or a whiteboard. We could write and publish an article, a blog, or a scientific paper. And just to look at this, let's look at how we consume this kind of thing in computer graphics. That's an area that I work in often. And so let's say you're a student, you want to evaluate an idea. You find a paper, you read this paper over, and you look for the formula. And you're going to implement this formula. So here we find this formula, and we want to implement it in C++. So we read the math. We have enough experience to know how this math should be translated into code. We write the code. And when we do this, it's easy to introduce a bug that we might not notice, right? I got the index wrong. That I should be a J. And that's going to be a subtle bug to find later. We might work with somebody else, or we want to do an implementation in a different language, like Python. So then we rewrite the same thing in Python. And this translation between the math and the code somewhere else, it's tedious, it's error-prone. It's also redundant, because people all over the world may be doing the same work. They may be implementing it and repeating the same work, and it's introducing different bugs. They think your technique doesn't work. They haven't even implemented it right. And then this is also tragic, because math, with the right context, always has an unambiguous interpretation, at least according to mathematical philosophers and linguists. And even worse, the formula in the paper sometimes has a typo. So here's an example where this is a typo that was published, right? Because the math is not executable. So let's look at the flip side. How do we write math? How do we write these scientific articles? So mathematical notation has evolved over the centuries. This is an excerpt from a table on Wikipedia. It's a really awesome table. You can see there's some nice texts and talks about mathematical notation. But we can see like the plus sign dates to the 1360 approximately. We're considered to be in the symbolic stage of math. We're out of the rhetorical and syncopated stages of math, where a lot of math was conducted with just rhetorical arguments. We have a lot of symbols, and we use these symbols. And a lot of the ones we recognize, plus, minus, parentheses, equal sign, multiplication, they get worked out from 1300s to the 1600s, and then summation, and then the linear algebra stuff. Actually, a lot of it comes in sets, come a little bit later in the 18 and early 1900s. So it's not correct to say that this notation has been fixed for centuries. It actually, a lot of it's fairly recent, but it is well established at this point. Now, if we want to write this math digitally, we have to get this into a computer. So to do that, we rely on markup, right? So here's LaTeX, right? Here's LaTeX or tech for those symbols, and some of them, right, the ASCII symbols, the ones that are on your keyboard, easy to type. They're there, but a lot of those other symbols have this markup, and the output is what we just saw, but the input obfuscates those symbols. We saw a trend in the mid-2000s of lightweight markup languages like Markdown, which codified these like pre-existing conventions people did when writing like text, like not math, but text. Like if I'm writing an email to you and I want to bold, and I want to emphasize something, maybe I'd put some asterisks around the word, right? And so that's what they looked at in Markdown and said, what are these conventions? Why don't we just promote these conventions into into proper HTML tags. And so you're getting markup out of existing conventions. What I'm showing here, around that same time, ASCII Math by Peter Gibson had a sort of similar idea. Let's do math without as much markdown. Just find something that we can parse. But some of the choices are a little bit unusual. I don't know anyone that would write XX to get a proper multiplication sign. Around that same time, right, Unicode's been invented. And so we can just lean on Unicode, and we can write a lot of math in plain text. Someone actually proposed a Unicode-based lightweight markup language in 2006, which is kind of interesting. You write what you see there. What we see here is what you do, so long as you can input the Unicode. Unicode entry is actually not that hard anymore. In Emacs, there's tech mode. In Vim, there's digraphs. On my Mac, I just go into system preferences and set up a bunch of text replacements. So Unicode's out there, and Unicode can give us nice-looking math. But this math is dead math. We haven't solved our executability problem. We can type math, but we can't. It's not doing anything for us. So that's what we set out to look at here. So that's this I Heart LA project, and this is joint work with Yang Li, who's a PhD student of mine, Shuaib Kamil, and Alec Jacobson. And I really want to make Yang's picture big here for a moment, because Yang is my PhD student who's done all of the work that I'm showing you today. I'm really just up here talking about Yang's work. So I'm deeply indebted to Yang, and want to credit him appropriately. So let's look at what I Heart LA looks like. So here's I Heart LA. And it's a language with syntax that's designed to closely mimic conventionally written linear algebra while still ensuring an unambiguous compilable interpretation. So you write linear algebra in text form, in plain text, and then we compile this. We take this and we compile it into TeX so it can look more presentable. But we also take the same text and we compile it into C++ or Python or MATLAB, and potentially other backends in the future. So to kind of put the space of different languages out here, so I Heart LA combines this conventional syntax with unambiguous execution. So those are two axes, and we can draw a diagram and plot things, right? And all programming languages, they have unambiguous execution, so they really just stick there up at the top, right? But you look at a math written in C++, and it does not look like conventional linear algebra, right? You go farther to the right with MATLAB and Julia. They look a lot more like conventional math syntax and Fortress and Mathematica, but we're trying to be as far to the right as we can. So it really just looks like what you would type if you weren't thinking about compilability, if you were just trying to communicate the math. LaTeX and ASCII Math don't have unambiguous execution, so they look like they may look a lot like conventional syntax, but they're just not compilable. Yeah, I'm not plotting up here some languages which aren't about linear algebra, like Agda, Lean, and Coq. They're about derivations, but a lot of them lean into this Unicode and math-looking syntax. So we're not the only ones to do that, but we're doing it in this executable math space. Okay, so to set about trying to compile and execute math, we have to decide we have to understand what are people doing, what are the conventions in mathematics, because although any mathematical formula has an unambiguous interpretation, a lot of context is needed to understand what the authors were intending. Right? So once you know what the conventions of their symbols are, you can interpret their symbols unambiguously, but you need to know what the conventions of their symbols are, and that does differ in different subfields of math. There's a very nice Math Overflow post by Terence Tao, who goes into 10 or 15 different notations for just writing a dot product, right? And that are used in different subfields of math. So so we picked a subfield, and it's the subfield that we often work in, which is computer graphics. And so we looked at all the numbered equations in SIGGRAPH 2019 and some of the unnumbered equations. So it's we generated this big body of about 2,000 equations, and then analyze them. We categorize the things we're seeing in these equations to know what's important and what shows up all the time. So here's a breakdown, but I'll go into this. So the first one to look at is single letter variables. So 98% of the equations are using single letter variables, which is like, when programming, I often got that hammered into me that we should not use single letter variables, right? We're encouraged to use long and descriptive variable names, but that's almost unheard of in conventionally written math. We can discuss the reasons why this is. We may not know the reasons why this is. I mean, this is up to the authors. Authors are making this choice, but this is like clearly established convention. It probably has to do with the fact that there is prose around the math, which is explaining the symbols, and that once it's time to look at the symbolic formulas, what the authors are intending to convey with these symbolic formulas is conveyed by what's happening with those symbols. And so the symbols themselves are just, hopefully you can keep them in your head and then make sense of what the operations are. So here are some examples of that. But one thing that lets you do with single letter variables is prevents ambiguity during multiplication, which is done typically without any operation between them. You just put two letters next to each other. So that would be confusing if your variables had were made up of multiple letters. So that's one thing that you avoid. But it's something else that we see. Yes.
Did you track how many use these descriptive subscripts, like the task and ISB in the top left? That's something I've used before, but I don't know how common it is.
Right. I don't think we have data on that specifically. Yeah, on that specifically. Yeah. But we do notice that like these decorations are very common, right? So not just the subscripts, but also over bars and arrows and hats and all these kinds of things. So people are decorating these things. Although these hats and these the subscripts and these arrows, those are a different role than if you make a subscript which is text. Or if you make a subscript which is text, you're basically inserting a long variable name, and that's true. Yep. But so let's look at the rules we chose for variables in iHeartLA. So here's a little bit of iHeartLA, and we encourage single letter identifiers, right? We also encourage Unicode decorations. This actually has we get juxtaposition as multiplication. We do that. We really want this to look like math. This has implications for the compiler design, and I'll talk about that a little bit later. But with Unicode, leaning into Unicode, we can get lots of expressive variable names with these text decorations, and as I'll argue, we shouldn't be so scared of typing Unicode on our computers. We're typing emojis a lot now, so we should also be typing Unicode. For long and ambiguous names, we also have a mechanism where if it would be ambiguous, we went with backticks like Markdown did, but they actually don't need to be used all that often in iHeartLA. Something else that a choice that we made is that variables can't be redefined. This is, in mathematics, in programming, people sometimes have this like, what does the equal sign mean in programming? Are we assigning or are we, doing equality? And, if we're doing equality, if you can't redefine a variable, this distinction sort of evaporates. Right? It's like you're defining x is equal to this thing, and x can never be equal to something else. So that distinction goes away. It's just we can't redefine variables, and so we don't need we don't need a different symbol for assignment versus equality. And something else you'll see here is that we have to have a type system. Since we're going to be compiling this, we have to have types. And so we have this type system, and then the compiler can do a lot of checking of what you're doing and tell you if there are dimension mismatches, and we can do this at compile time. Just statically check: can you multiply these matrices or not? So let's look at matrices a little bit more. This is like a syntax we have for matrices. So you don't need commas. You just put what you want in the space that you want it. So that's on the top left. Let's look at this example on the top left. So we have in the diagonal, we have A and K in this case are scalars. So this is a 2 by 2 matrix. L is just a normal 2 by 2 matrix. On the right, we see in the counter diagonal, we see M is being used in X and Y, and those are matrices and vectors. So this is a block matrix, and the identity matrix and the zero matrix are getting automatically lifted to be the right dimension, because there's only one correct answer that can actually make a matrix for this using these blocks. The identity matrix has to have the same number of rows as M, and it has to have the dimensions as the number of rows as M, and the zero also has to have this the same number of dimensions as the rows and columns of those blocks that it's adjacent to. So this same syntax gives us a nice way to input these matrices. And we can, we also have notations for sparse matrices. So you see, mathematics, you can write these underscore and L underscore ij, and we're defining the entries of I and j. And again, with single letter variable names, we don't even need a comma, between the I and the j. So we get this, syntax which, is that we're pretty happy with. So over here, the dimensions of L is determined by the dimensions of M, and on the right, we're defining a sparse matrix, and it's got a conditional, and we don't know how big L is. We don't know how many zeros it might have, on the right or on the bottom. So the author does need to say what the total size of L is. Okay. Something else that a lot of equations use is functions that are not defined in the paper. So we have to have a way to talk about externally defined functions. Here's some formulas that show up, and here's like examples of these functions which show up everywhere, right? These expressions don't exist in isolation. So some of these functions are just well known, like trigonometric functions. So sine, cosine, and other trigonometric functions. Those are just like you expect them to be there. So we allow people to just pass in functions in all the languages we support. You can pass in these functions, and you have to provide a mathematical type annotation for them, but then you can use them. And we also have some built-in linear algebra and trigonometric functions that you can make use of. Summation is kind of an interesting case of a mathematical operation. So in papers, we often see summations that have implicit ranges. So there's nothing saying where to start and stop iteration. Summations can be nested, right? So double summation inside of a summation, and they can be part of larger expressions. And summation doesn't enclose the thing it's summing over with a parenthesis or with a bracket or with anything, right? So we have a choice to make here. It's kind of ambiguous. When should you stop summing? So to make this really clear, here's what seems to be a simple summation, but there's two interpretations. Are you summing just the AI and the BI, or are you also summing up a bunch of copies of C? And this could be arbitrarily complex. You could have a second summation to the right. So to make a decision on what to do, we looked at what are people doing, right? So we want to be compatible with what people are doing. So we looked at examples, in Wikipedia and again in SIGGRAPH, and here's a bunch of formulas, from SIGGRAPH 2019. And when we look at these formulas, we see most of them are taking the conservative summation choice. So they are putting parentheses if they're summing over more than just one parameter. Other than these two. So with this conservative summation, we seem to match what most people are doing, and that seems to be like the reasonable trade-off space that we're happy to exist in. So which is to say, we take this upper path and infer bounds from use. So you get to write your summation, and because wi and ti appear here, then the summation is going to iterate over all the elements in that thing. And hopefully eliminate some mistakes in papers where people got the summation bounds wrong in their summations. Okay, so norms also show up a lot in 14% of the equations, and this is a bunch of different kinds of norms, L2 norms, so squaring things, L1 norms, Frobenius norms of matrices, nuclear norm occasionally shows up, vector norms with matrix subscripts. So we can, we can support all of these, put all of these in, and just support all the norms we can find. So let's look at the compiler, right? So that's like an overview of most of the pieces that we support. And the compiler, starts with some I heard LA source. But in this example right here, if we do our first pass on this compiler and we can look at all of the terms and the symbols, but we need a second pass. And the reason we need a second pass is we need to know what the types of things are. In this case, this f of x squared, if f is a function, then we should be squaring the result of the function. So the square should happen after we put f of x together in a node. But if f is not a function, if it's like a scalar, then we should square x first and then multiply it by f. And this, we have to have a two-pass design to do this. We also need this, when we take in external functions like sine and cosine. Those aren't single letters. If anytime the user does define a multi-letter symbol, we also detect all of that in the first pass. The first pass is just parsing out all of the symbols and what their types are. And then the second pass can correctly build a correct abstract syntax tree. And then, we do code generation, right? So we've written the C++, which is a static language. We've done Python, which is a dynamic language. Those are both zero-indexed. We've done MATLAB, which is a one-indexed language. We've done LaTeX because we want the same I heard LA to be used authoritatively to generate the equations that you put in your paper, and then also the code that you can distribute, that everyone can run and try. And we want to extend this to other languages in the future. So let me do a live demo. Let's see how big that is. That is probably not readable. That's readable, but is that readable? Either we go with this or we go with this, but then we lose that we have to scroll to see the beautiful version of it. Yeah, so this is an example. Here's a matrix, right? This is a column vector, and you can see we're using this Unicode superscript 7, which we can type, any superscript we want. It's, do text replacement. I really am passionate about the point that it's not so hard to type Unicode into a computer. And you can use this symbol for multiplication of two numbers. So this is we compile this and we get, compile succeeded. And you can copy any code you've got as a URL, send it to a friend, they can paste it in, and, they get back exactly the example that you had just typed. So it's, pretty easy to share. And, you can just scroll down here and just copy and paste out, the output from any language that we support. Let me type in some more examples. All right, let me do. Let's implement dot product, right? So let's do a summation over I of two vectors, AI and BI. So let's say AI is a real. Let's see, how long is this vector? Let's say it's an n vector, and let's say BI is. Let's say it's an m vector. So this shouldn't compile, right? Because we have different dimensions. Well, I really hope this doesn't compile. Right? And we get an error, the dimension mismatch, right? It can't multiply an n and an m vector together. But if we correct the type, we say that they're both dimension n, and we compile it, and we get... No, that's... Oh, right, I'm sorry. Oh, okay. Each element of A and B is a real number. So that works. This is awkward. Yes, I'm defining the syntax. I'm defining the elements of a sequence. If I wanted to say that A is an n vector, I should have said that, and B is an n vector, and then this should compile as well. Okay, so we have sequences. It's not always easy to write math, folks. Sometimes we make mistakes when we write math, but at least we have a compiler now that's going to be catching our mistakes and telling us when we're doing something that we didn't expect to do. This is a teachable moment, right? I just tried to multiply, like scalar multiplication, 2 vectors, right? And if I really wanted to multiply 2 vectors, I should have put in like a dot product, right? And said, okay, each element of AI and BI is an n vector, and then this should compile as the sum of the dot products. Yes, I saw some hands. Yes.
In this case, what is the domain of summation?
So it's going. So it is defined by the input length. So if we scroll down to the code, let's look at the Python code. So we can see that it's summing over the length of b, whatever that is. Right? Like we have not defined the length of the sequence. It's like these are dynamically sized sequences. Is that the?
Well, I guess it makes sense that if A and B were vectors and you did a sum over I of A sub I, then it understands that I is indexing over n.
Yes. Yes.
But in this case, it doesn't make. I guess it's not obvious to me how you would pick some sensible value of I here.
Right. So at some point this has this gets converted to to code, right? So let's say in C++ you're passing in a vector, right? So at that point, right, the code can get the size of the vector and iterate over that size. It's a sequence of some indeterminate, but indeterminate, like of an arbitrary size that is general to the length of that sequence.
But if AI and BI were just reals and then you were just doing multiplication of them, it still picked a value of I. What was that?
So sorry, in this case.
Yeah, and then AI and BI were both reals. It still picked a value of I, right?
Right. This is, so let's start with this one. This one, if we look in C++, right, we've got a vector of doubles for A and B, right? They must be the same size because...
Why are they vectors? Did you specify that they're reals?
The elements are real.
The elements of the vector are reals.
Oh, I see. So it's not, it's changing the interpretation of them to still be like, these are still elements. Okay.
Right, because of the subscript on the left-hand side. Right. Yes?
Can I convert Python to iHeart?
We would love to do that. The inverse problem, right? Go over all these code implementations and factor it into linear algebra, and then that we would love to do that. We can't do that. I don't know how to do that, and that's not unannounced future work that we've already done. Yeah.
Your initial assumption was we used to write math but now it's like I have to write math on a computer again. So maybe on your first point that you're not an expert in computer vision, maybe that part could help, no? You write the math, you convert from that language to maybe this can be the translation moment.
Yeah, I think something that's a little more doable. So there's like programs like MathPix, right? And they'll you can take a picture of math and they will give you LaTeX for it, right? And so that's going from math to a LaTeX representation of math, which is ambiguous, right? But if it's like a subset of LaTeX that's we can convert to iHeartLA, right? That would be a pathway that I think would be, famous last words, not too hard, right? But I think that would be a pathway to do that. But going from like code, right, which is where the semantics, of the data, the types, the high-level types, the linear algebra types have been lost, and you're just taking in, vectors of doubles. That's, that would be great. That would be great. I mean, there was I think the Halide folks did it recently. They have this like MetaLift system, which they've used to, take like Adobe's code base of C++ and like turn it into Halide, and they can recompile, for new architectures, and that's like production strength. So it seems like the technology is it seems like it's worth I'd love to do it. Yeah. Was there another question before I go on? Okay. Let's see, another example I should give you. Well, this is, maybe some of you will enjoy this. So this is a case where, we have 3 different matrices, and again, we're going to check the types of these matrices are compatible, for multiplication. If I make this 5 by 5, right, we're going to get an error that the dimensions mismatch. But one thing that's, that I'll point out is in a static language like C++, I don't know if any of you have used, Eigen, but in Eigen, it's very easy to make an arbitrary dimensional matrix, and then the memory is, dynamically allocated and iterated over, with dynamic loops. But if you give it proper static matrix dimensions, I think it can do stack allocation, and it can, generate at compile time. It knows, the loops it should do, and so the code would be more efficient. And it's very tedious to do as a human, right? But we have a compiler here that can do all of this for us, right? And so it can, put in the exact type dimensions and also the output dimension. So I should say we really are not interested in high performance, high efficiency code here. I mean, that's been a non-goal. I wouldn't say we're not interested in it. We would love it. But it's our goal is not to say this is the code which is production ready. It's as optimized as we hope to be able to do. There's a lot of work out there on highly optimized linear algebra and tensor math, and people doing a lot of work in that space. We want to generate something which is like you can evaluate the idea and decide whether it's worth putting additional resources into doing like a faster implementation. But there's potentially a nice interaction there, where we can output this linear algebra intermediate representation and interface it with these other systems which are doing high performance stuff, and get I don't know, maybe the best of all worlds. Right, I want to show another example here. I've shown some sparse matrix things, but I want to show this example. This one points to something which... So this is the matrix form of evaluating a Bezier curve. Let's pretty these up. Let's get more Unicode. All right, so this is the matrix form of evaluating a Bezier curve at an arbitrary point along the curve T in any dimension, right? So this is it's a cubic Bezier curve, so we have our T cubed, T squared, T and 1. Here's the matrix of coefficients. Every different cubic spline or every different cubic curve has a different matrix like this. So you change these numbers around, you change the meaning of what the control points are giving you. I'm bringing this up because this shows that we have this 2D. You can make 2D matrices, but we don't have a solution for where the line, the line continues at the end of the matrix, right? It would be really nice if like P could be up here, So if you had like another big matrix, right? If you wanted to put another matrix, this is no longer doing what I said, but put another matrix here, right? Like this, the math really starts to bleed onto multiple lines, and we don't have a good solution for this. This is just we consider this I don't know. This was the trade-off we came up with for plain text math, in a linearly encoded text file. Like non-linearly encoded, math is very interesting, and if you have ideas about that, be happy to talk to you about that.
Well,
yeah.
Couldn't you define each of the matrices as a variable and then just multiply?
Oh yes, absolutely. Yeah. Right. We could just say, I could just say m equals, this, right? And then right. And then this is just now, m, right? Here, let's just make this like that. Right, and whoops, symbol m. Oh, right, that's out of order. Which we now, it's not in this online version, but we do, because we have the single static assignment, in our current, in the non-web version that we've done, you can actually put things in any order, and it just figures out the right order. But that's not in this demo, right? So yeah, so this compiles, right? And this is, this is nice on the same line. We could square this. Right. But let me switch back to the slides, and I'll show you some other examples, and we'll see how this comes up sometimes when converting formulas that are out there. So we want to evaluate this, right? We came in saying, okay, we've got this. We looked at math. We can compile math, and we want to know what conventions people were doing, and we want to know if we've succeeded, right? So to know if we've succeeded, we want to know if it's useful, right? And so one of the ways to know if it's useful is to collect a variety of examples from in the wild, right? So just collect a bunch of examples which show the breadth of the kinds of things we can do. And so for each of these examples, we have a gallery, right? And you can compare the math. This is a screenshot from the paper. This is the math that we write in iHeartLA. Sometimes there are some small differences, but we try to minimize those. If we've succeeded, we've minimized those, I would argue. And then for each of these examples, you can go and browse around in our pages and see the C++ and the Python and the MATLAB code and all of this. And let me zoom in on a different example. This is unplanned. Where is it? Right. This example down here at the bottom. Oh, you're not seeing this because this is unplanned. Right. So this is an example where somebody wrote a very very long equation, right? And in in iHeartLA it ends up kind of spanning 3 lines, right? I would argue this is fine. I think one of our reviewers thought that this was that the input equation was like the problem. That this was a sort of pedagogical punishment because this comes from a course for students to make students have to read something so long. But that's an example where that comes up, as just having to just end up spreading across multiple vertical lines. So another way to evaluate whether we've succeeded, right, is to take the output code that we generate. Yes. Yeah.
It's interesting. So, have you thought about line breaking in appropriate places? It's probably worse to line break between 2 variables that are being multiplied rather than other places in the equation?
Yeah, so the only line breaks we had there were in 2D matrix definitions.
I see. Okay.
Right? So if you put a line break anywhere else, you're ending the statement.
I see.
Right? So it's these 2D matrices where we want to have a nice, beautiful 2D arrangement, no commas, no semicolons, We do actually support like semicolons if you want to put it on one line. That's a choice that MATLAB does, but I don't even like that we support it, because I don't want things to look like weird MATLAB, programmy math. I want things to look like, like math, like you would want to write it without constraints, given like a chalkboard or a 2D writing surface. But we just parsing 2D, we thought about okay, you could put closing brackets on each line. There actually are Unicode symbols for all sides of a matrix. So you could, upper left, bottom right, upper right, bottom left, and then vertical bars. So you could potentially do something there where you go, okay, well that's a top right, an unclosed matrix, so it must continue down. But it just starts to get messy, and it's the trade-off feels like. We didn't pursue that far enough to know whether it's there's you end up with something that works nicely, and So another way we want to evaluate this is to see if we can integrate with existing code. Take our code, see if it's useful. So we went to found a bunch of papers and that had code online, right? And these papers produce these pretty pictures, and then we went to we want to simulate using iHeartLA in the real world. So open the paper, find a formula, take that formula, write it in iHeartLA, take the output code, replace code. In this example, find the paper, find the formula, find the code in their code base, write the formula in iHeartLA, take our output code and put it in the formula. So let me simulate that, right? So here is somebody who wants to implement this paper, right? So they're reading this paper. They say, okay, there's this formula in the appendix, and I want to take this formula, and I want to try it out. So they find the formula, which is a simple solution for this constrained least squares problem. And they go and they open the, here's the formula. They open the iHeartLA, editor, and they start, they have their code base and they have a space for it, but they need something to put in to fill in here. And they have, the input parameters are all prepared. We just need, an implementation of this formula. So in this case, those subscripts are like not actually subscripts. They're like decorative subscripts. So that's one place where the backticks end up getting used to just not tell iHeartLA that we're defining sequences, to just tell it these are just like parameters with weird names or with subscript names. And you get the code, you find the code, you go and you paste it into the right place. Compile it, launch the program, open the mesh, and then solve the equations and get your instant field-aligned mesh using code generated from iHeartLA. And we verify that we get the same thing that the implementation the paper authors got. So, what can we say about this process? So one thing we notice is the line, it's less lines of code. Typically, the iHeartLA is actually, pretty terse. But also importantly is it's no longer just C++, or Python. It's any of these languages. And something else we wanted to do is understand statistically, because, we can be accused of cherry picking, and it's essentially, we are cherry picking, right? Like we're finding examples with code that we can, implement, right? There's like an aspect where it's like it's hard to separate as a scientist what's like this is not, double anonymous. Like this is like we're picking examples that we think will show our work, right? But now we want to do something that's that we can't control, right? So we roll the dice once. Right? We take all our 1987 equations and we shuffle them and we take the first 100 and we don't get to do this again. We don't get to keep doing this until we get numbers that we like. We do this once and we take these 100 equations and then we categorize them, right? So looking at them, 53% are just plainly implementable, right? Another big chunk are derivations that aren't meant to be implemented, right? Then some of them use partial derivatives and gradients and some kind of unsupported integration. Some of them have complicated optimization, some control flow, and some other kind of strange operators. Now, really, the derivations are not meant to be implemented, so we should just exclude those. No one's implementing those in any language. So now maybe we can implement 62% of what we see. And then, okay, we don't support automatic differentiation or taking gradients, but sometimes those are passed in as parameters in optimization packages. They expect you're passing an F, so give us also the gradient of F. So we can also have authors do the same thing with iHeartLA, or give us the gradient of F as a parameter. So in some sense, we can also, we could also support that. Maybe that's the unbiased, non-cherry-picked applicability of iHeartLA. We also, did a user study, so we want to know how people use this. So we took 8 CS PhD students who had, over 6 months of experience implementing linear algebra, and we gave them 3 formula, and we said, okay, you have a preferred programming environment, the one you like to use. Okay, you're going to use that, and you're also going to use, iHeartLA. And we counterbalanced it, so it's like 2 in each condition. And then we gave them, sequence of problems. Simple one, just do some matrix vector multiplication. More complex one, use summation, and then most complex one we gave them was to build a sparse matrix. And we got some qualitative data out of this. So one thing we got, Likert, 5-point Likert scale. So people want to please us, sure, but they say it's easy to learn to use iHeartLA. And a lot of them, preferred it to their programming language. And maybe, the nicest thing out of this is that, people agree that the iHeartLA looks like linear algebra in the papers they see. So, this is a small study. They're trying to please us, sure. So maybe we don't get strong conclusions out of this. But, at least when we look at some of the quantitative data, we can make some statements, right? So average completion time, they're faster in their language for the simple problem. And that is statistically significant, even though everything's a small number of people. For the medium case, things were closer, and for the complex case, one language wasn't faster than the other. We take that as encouraging, right? This is their first exposure to this language, and they can already, implement things at approximately the same speed as their language, and so that's, I think that's encouraging that they can accomplish a range of tasks in 15 minutes, and they think it looks like conventional math. Yeah, so some limitations. So I talked about the kinds of things that we don't support, right? So there's, mathematical operators, right? We don't support. Multiple conditions. We actually now do support this, but that's new. This is like, go file a GitHub issue if you have something that's not supported that you want to support. Derivations, right? We'll never support. Well, I shouldn't say never. It would be nice to not have to switch languages when writing, to switch from IRLA to TeX. Maybe we could have a non-compiled version of IRLA that doesn't compile the code, but just like gives you TeX, so you don't have to keep switching, your mental mode for inputting math. Derivatives we don't support yet. Optimization I'll talk about in a moment, and integrals we don't support really. We support some, not with implied domains. I'll talk about that right now. So we'd like to support more things, tensors, automatic differentiation, integration, optimization, and there's a lot of work out there, right, on automatic differentiation, and some recent work on integration with integrals, with discontinuities. So that's just like, file the GitHub issues. We'll see what people want. We want people to adopt IRLA. Minimization shows up in 10% of the papers. So we wanted to make sure we weren't going to make a grammar that wasn't like future proof in some sense, because we do want to support more minimization. So we already support a kind of minimization. So we can do some constrained minimization, and we rely on in Python, we rely on SciPy's optimize, to do this. So in C++, we need something, because we don't want to start implementing a whole bunch of numerical routines. We want to, just compile to these output environments. So we have some minimization support. We also have some integration support for simple integration with upper and lower bounds. Two styles, right? You see people in math write it in both styles, so we support both styles. We want to do more advanced version of this, and again, we just rely on what's there in the language. Now, I want to increase adoption of IRLA, right? So more output languages. That's kind of like straightforward. It would be interesting to embed it into your tooling. So if you're in C++ and you just want a bit of IRLA, to kind of make it so that you can do that. Julia has a nice macro system, so maybe you could do that there. Supporting more fields, looking at what they're doing in their equations. Large-scale user studies, get people to use this over long periods of time. Does it make people more productive? Can we give a set of students or practitioners an unsolved research problem with a measurable outcome, and have some of them use IRLA and some of them not, and see if they improve the state of the art faster with IRLA? Automating, TeX to IRLA would let us do the kind of math picks, to TeX to IRLA. Also, papers of the future, right? If you imagine a paper of the future that's using IRLA instead of, TeX for math, then this paper could compile to a library for improved, replicability, but also improved interactivity, right? Like a notebook environment where you can interact with the equations that are in there. But also the type information that we have, we know what all the symbols are and where they're, the same symbols used in multiple places. So we can do something for readability, right? There's some recent work, like the Scholar5 project, where they didn't have IRLA, but they kind of went through with natural language processing and kind of heuristics to do things like give you a glossary of symbols and break down all of the terms that are used in an equation, right? And So it would be really nice to make a writing environment that uses IHEART-LA that gives people like them the information they need to make the system work, correctly and always. But just from our point of view of trying to take existing conventions and meet people where they are, we'd like to have minimal impact on the way people write papers, right? So something plain text, right? Again, the derivations, like here's a bunch of derivations in orange, and then you get to the the formula, right? So having to handle that. The out of order symbols, this is showing like a symbol that appears early in the paper depends on the later symbol, which itself depends on the later symbol. And we do this because I guess as authors, we want to explain the high level thing first, and I'll tell you the details later. You'll need to know them, but not yet. And then like I talked about a library, but like what would a library be? When people write functions in papers, there's often like a lot of implied parameters when they're defining functions. So, and the symbols may appear in different contexts, but that context may be clear to the reader that the x here, the xy here is different from an xy there. And finally, like papers may be, multiple sections, subsections, which are largely independent. Right, so to conclude all of this, I believe that IHEART-LA has the potential to greatly benefit the scientific ecosystem, right? The way people write papers. No one wants a replicability crisis in their field, and I think this can, this has a role to play there. I think IHEART-LA makes it easy to try new ideas. Just write that email and then execute that email rather than spending time implementing it. It's pretty easy to learn because we're just trying to take what people are already doing. And then finally, we want to reduce the translation loss as ideas move from researchers to writers to readers to implementers. So a graduate student, describes their implementation to a co-author who writes it in LaTeX, introduces an error, but then someone else reads the paper and implements it incorrectly. And that's something that we don't want to, that we think we can reduce. So thank you for listening, and please try out IHEART-LA and let us know what you think.
Great, we have time for questions.
Yeah, sure.
I wonder if you have explored maybe simplification of like equations, or maybe breaking down a very long equation into maybe multiple sections for readability.
Yeah, that's an interesting idea, right? We have thought that sometimes like an equation is in a paper and it's like not exactly a formula where there's something on the left hand side equal to something else, but it's close enough that maybe like a reader makes these steps, and like there are these symbolic algebra packages that may be able to help, right? Like factor it to simplify it, or solving for in simple cases. I think there's something we could do to leverage work on this on symbolic algebra and symbolic manipulations but we haven't thought a lot about that case of like breaking it down to make it easier to read. Yeah. Thank you. Yeah.
So someone also interested in the human factors of scientific communication, I found your formative study really interesting because it's this form of notational survey, essentially. And it's about, and I'm curious just to hear a little bit more about your methodology. Like you presented with 1,986 equations, and you need to do some kind of semi-structured look through these things to find out interesting stuff. But how did you structure that process? Like there are lots of aspects of these equations you could consider summarizing or annotating, but what guided you to decide that this was an important factor to look for and therefore to ultimately inform the design of IHEART-LA?
Yeah. So there are other attributes that we categorize that didn't even come up here, right? Like looking at like who's using superscript and who's using max and who's using I don't know. I don't remember them off the top of my head, but it was basically like a brainstorming, looking at equations and brainstorming and saying like, what are all the weird things that show up, right? So I think Yang again did a lot of the hard work here, right? So he's the one who went through every SIGGRAPH paper and like took screenshots of every equation and put them in a giant table, and I think there was just it's just like, did something weird come up? Like let's make a new category for it, right? And then just try to enumerate all of the math that's used. It's error prone potentially, right? Like maybe you miscategorize something or maybe you misunderstand something. This actually came up in one iteration where like we had examples and then a reviewer would say, I went to look in that paper and you got the type wrong, and so you're making mistakes, and so how can I trust like what you're doing or something like that, right? But it's like to actually implement these correctly, like without, this is like almost a chicken and egg thing. Like if the paper had been written in iHeartLA from the, in the first place, the types would have been really apparent, of every formula. But like skimming a paper, reading a paper, it's easy to make, to get that wrong, right? And then potentially to implement it wrong. Yeah.
So it seems like you have sort of two different use cases here. One is helping authors by using the type checking of the generated code to find bugs in their writing. And I'm curious if you did any checking of the equations in all those papers to find how many of them have bugs in there.
Yeah, right. There's the example, early on where it's like a clear typo, right? Right. Some of the questions we'd like to answer are almost equivalent to like implementing every SIGGRAPH paper, from 2019. Like, well, okay, we have this data set, like, let's just like go and try to implement it, and it's like, it's at some point it's like, that's like too much work. That's like too much work to go through and implement everyone's thing. But some of them we have to like chase. We actually did like have to chase down for quite a while. There were like some papers. There's one paper where we end up finding, 3 different versions of it because it was really confusing, to understand. Like they're reusing the same index, and a few summations, but the length of the vector was different. It was a different dimension, and then like the description of what that dimension was supposed to be, because it didn't have a upper bound, was like in different places in the paper and was written out in prose and in a way that was like, kind of a summary, right? And it's like took a lot of tries to make sense of it, and I hope we got it right, but it's like I don't know, basically. I don't know how many of these papers, have mistakes.
Yeah, but it's sort of embedded in that answer. There's this interesting question about why it takes so long to implement it in iHeartLA, right?
Yeah.
Because the equation is written, you just start translating it into your syntax.
Right. It's the types. It's like saying like how many dimensions is this thing?
Right. So going and finding that thing.
Going and finding that thing and getting it right. It's like, okay, is this a scalar or is this a vector? And if this is a vector, is it the same length as this other vector? Or is it a different length? And so it's like that information ends up being actually scattered, pretty far apart in the papers. Or the paper in question was like it ended up being like a 23-dimensional vector where it had like camera parameters as 6 of the dimensions, and it's like, well, how many dimensions are in the camera parameters, right? So you have to go through like multiple levels of indirection in the prose to finally nail down what the dimensions of this thing really is, Right.
So I was saying before that there are 2 use cases here. One is for authors and this type checking, it seems like, and the other one is implementing the code. And they have slightly different goals, or maybe fairly different goals. And so I was wondering if you are thinking about how those goals differ and what you might do to address them separately.
Right. So some of this is like, sometimes when you write a paper, I don't know if I'm revealing like a secret, of how the sausage is made, right? But sometimes like you've done all this, like you've coded something, and then you've made changes to it, and you've made changes to it, and you've made changes to it, and then it's time to write the paper, and you want to write something that like maybe seems elegant, like reasonably elegant, and maybe not like the spaghetti of code that's like eventually resulted. And so you're trying to like, come up with an elegant way to phrase what you've written, that still matches what you've written, right? And that's sort of the translation loss, thing that I'm getting at there, right? But like implicit in that is the fact that like you're not working with a nice, clean mathematical, you're not like updating your mathematical formula the whole time and then trying it. You're actually in this other like coding space, programming language space where you're making changes, and then if you then like write it in, I don't know, an iHeartLA and then compile it and run it, and then, I guess you could check if you got the same thing as what you had written or not in, your spaghetti code version of it. But like, there's another, world, I guess, in which iHeartLA played a role in all of the experiments, right? And that's like a different thing, right? That's like oh, if we can make it so the email or the blackboards, were like authoritative, the whole time, that is a change to how people work, right? So I guess I'm trying to have my cake and eat it too. I'm trying to say, we don't want to change how you work. We just want to like make things work better. But like, I really do want to change how you work, Yeah.
All right. I think we're out of time, but thank you so much.
Thank you for having me.